Basically what we're going to do here is try to implement some of the stuff that Dafna taught you before the break. So again, we're doing NLP for medicine, and here we have this toy data set that is taken from a Kaggle competition. This data set contains, well, a lot of data, but we're going to use only a part of it, and the part that we're going to use contains transcripts of people describing their conditions in one sentence, and the label itself, which is the condition. So we have here examples. One example is, I have a dull ache in my lower back, which makes it difficult to move, and the label is back pain. Another example is, when I think of my parents, I feel pain, which is emotional pain. And another example is, I can't move my head up and down, which is neck pain. So that's basically how the data looks like. Now, the data frame itself, the file contains more than just these two columns, so we're going to clean it. And basically it contains more columns that are relevant to the audio part, because the original data set is for a competition about speech recognition, which is a much harder task, and we're not going to solve it now. And basically we're going to learn here some embedding methods, bag of words, which is very simple, word2vec, and Vert, which is a pre-trained language model. I'm sure you've all heard about ChatGPT. Yeah, okay, I see the nods here. So that's a pre-trained language model, a very strong one. So BERT is basically very simple in many aspects. And because it's not really oriented towards machine learning, we're just going to use one classifier, which is random forest. Now, is anyone here not familiar with random forest as a classifier? No, okay. But if you're not, just, tell me. So we're just going to use it, but it's plug and play. We're going to use sklearn. You can use whatever model you want to use there. Again, that's not really the essence of what we're doing. So I'm going to run it here, and I'm going to say that originally you were all supposed to get permissions to the server of Shalet Tzedek, and then just everything was supposed to be there, but that didn't happen. Again, some technical problems, so you're going to do that on your laptops while I run it here. Is anyone having any problems with either getting my email or keep installing all of these packages? No, okay, no problems. Okay, so basically I assume you all install the packages. You don't have to run it while I do that. You can play with that afterwards and just listen. And we start with exploring the data set. So we import pandas, which is a Python package for manipulating data frames. It's super easy. It's basically just work with CSV files, which are Excel file, and we import matplotlib just for creating these beautiful plots that you're going to see in a second. So we read our data, and if you already ran this code in your laptops, you're going to get the path error. Yeah. Exactly, because I have this in a folder named data, and you do not have it because I just sent it through your email, so just delete that part, and then it will work. Okay, so now let's explore our data set for a second. I just plotted here the first 3 rows in my data set, and I see there are a lot of columns, a lot of things that are not very relevant for our task. And the thing that is relevant is phrase column and the prompt column. So again, that's very similar to the examples we had. When I remember her, I feel down, and the prompt or the label, the diagnosis is emotional pain. And we have here, when I carry heavy things, I feel like breaking my back. And we have here the label hair falling out. Does that feel right? No, right? So we see that we have some mistakes in our data set. But nothing's perfect, and that's just something to keep in mind, that it's not perfect. So the last one, there is too much pain when I move my arm. Again, heart hurts, not perfect, right? So there are problems with the data set, but we're not going to fix it right now. So we have overall more than 6,600 different rows or data points in our data frame. And the columns are all of these. Again, we're just going to look at the phrase and the prompt columns because we don't really care about the entire audio speech recognition problem. So let's take a look exactly at these two columns that we care about. Now it's much easier to read, right? Again, you don't have to run, you just look here. So we have, when I play football, I have joint pain, and the prompt or the label is joint pain. Okay, that sounds fine. When I tried to take care of my hair, I found that it's falling out, hair falling out. Okay, so it's not as dirty as it seems when we looked at the first 3 rows. Now, there are duplicates in the data set, and I say that because I looked at the data set and I saw that there are rows that repeated themselves. But even if I didn't look at the data, it's a common practice to just drop the duplicates. So that's what we're going to do, and we see that there are a lot of duplicates here because we're left with only 700 different unique data points. So why do we want to drop the duplicates? Anyone? No idea. Sorry? So no new data, that's true, but why else would I want to do that? It might affect the frequency of my labels too, right? But you know, the most important part, in my opinion, is the fact that I want to teach a classifier, and I don't want to have leakage from my trained data set to the test data set, because then I get a distorted image of how well my classifier will actually generalize to unseen new data. So all of these answers were correct, and the core one is actually data leakage. So let's see how many different classes do we have and kind of plot them. So on the x-axis, we see the different classes, different labels, and we see here the counts. In order to do that, I just use the matplotlib. It has a method plot, and I created this bar plot. Okay, so that's what we see here. Okay, seems pretty nice. Now, did Dafna teach you about word clouds? Because I was having these technical issues when she talked. Okay, so I'm gonna use this package, word clouds, and I'm gonna just take all the values of the phrase, basically all the words that people used in order to describe their condition, and I'm just gonna, you know, join them all because that's how the library works, and create a word cloud using this library. Now I want to plot it again. Matplotlib is perfect, and here we see. Okay, so the size of the text is correlated with its frequency. That's the whole idea of word cloud. And here we see that words like feel and pain and back and hurt are very frequent. But what does it tell us? Nothing, basically. So what we want to do is maybe look at these word clouds of the different classes and see if we can detect different words. So I created here a function that basically that's what it does. It just takes the text of, it takes the phrase text, the condition, the text where they describe their condition in the place where the data frame is equal to a label, a specific label, a specific prompt. That's basically the function. Again, let's just look at our list of different labels, and let's take, for example, cough and plot it. So now we have the word cloud of only this specific class. Does it make sense? Yes, no, maybe. Yeah, makes sense, right? You see cough and you see throat and cold and coughing, which is another problem, right? Why do we have cough and coughing? Maybe we want to merge them because it basically has the same meaning, right? So if we'll have time, we'll do that. There are two different methods to do this combination. One is lemmatization, basically taking all these words into their lemma, which is without the ing, without the s, and everything, just a simple form, and tokenization, but we'll see if we'll have time for that. And if we don't, so you have this Jupyter Notebook lemmatization, which I attached in the mail, so you can explore that later on. So we'll see. Let's take a look at emotional pain. Does it make sense? You can actually say words, you know. You can talk. No, okay, we don't want to talk. So yeah, it makes sense to have all these words, feel, pain, sad, hurt, when you're talking about emotional pain. Also, you have here stuff like parents and partner, which are major reasons for why we experience emotional pain. Yeah.
I have a different map here.
What do you have?
A different map.
A different word cloud.
Yeah.
Yeah, because there's some random initialization in that. But basically, you should get similar. It looks different, but the frequency itself is the same. And then if you rerun it, you'll see something different. I can actually do that.
No,
so.
it does well because I don't have the word husband, I have girlfriend.
But you don't have it at all?
Yeah.
So you can actually look at...
Yeah.
So
what's stochastic? That's what I know.
Just a second, word cloud. You can just look at the words themselves.
Oh. Yeah, maybe it's the max load argument. Yeah, maybe the max load argument just cuts off it.
Yeah, so it does cut it. So if they have the exact same frequency, it might happen, and you can actually look at the words fitted, but you can play with that. Yeah, so if you rerun it, just for a second, let's do that, you get different plot. But the frequencies are the same. Okay, so feeling dizzy, just the last one, because we're having such a great time. Again, dizzy and stand and morning and start, things that do make sense here. By the way, I did see here break. You see an emotional pain break, so it's probably break up, but we didn't fix for things like that. It only separates for single words. So that's something you can actually change in the function itself, but we're not going to do that. We're just going to move to the NLP part, and we're going to talk about text embedding. Now, Dafna presented the notion of text embedding. It's basically a vector representation of our text. It can be a vector representation of the word, a sentence, or an entire document. And the whole idea of text embedding is that we create this embedding space or latent space that is supposed to be meaningful. For example, Dafna showed you the word to back, king, queen, woman, man example. That's a very classical example showing that in this word to back latent space you can do these arithmetic operations and get something which is meaningful. We're actually going to see that in the code itself and not just in a PowerPoint presentation. But first we're going to start with the simplest embedding method, which is bag of words. So, do you know what bag of words is? All of you? Okay, no, perfect. So we're going to talk about it. So bag of words is basically an embedding method. How do we do that? We have this corpus, or just, this text file, and we start counting all the occurrences of the different words in our data file. So for example, let's assume that this is our data file. All of these sentences, it was the best of times, it was the worst of times, it was the age of wisdom, it was the age of follies. And then I just split all of these sentences into the different words that I have. These words are going to be my vocabulary, all the words in my model. And now I'm going to count how many times I see each of these words. And for each sentence, I'm going to basically create this vector saying, okay, which words appeared here. So the first element in the vector corresponds to the word it. The second one corresponds to the word was, and that's basically the order. Let's look at foolishness. I see here 0. Why do I see 0? Because it's not in the sentence. Great, perfect. And here I see 1.
You do it for each word in the sentence, even if it's like time and times, it's not the same word for in the metaphor?
So basically what we usually do is this kind of pre-processing where we do this lemmatization that I just said. We take each of these words into its simplest version. So we remove the S in the end of a word if it's for plural. We remove ing and we remove all these things. We also usually remove what we call stop words, which are just words that are kind of meaningless, like are, am, is, and stuff like that. So we do have this kind of pre-processing phase. Now it usually happens automatically. You don't really have to think about it because most of the methods already implement that. So we basically have this bag of words that doesn't care about the order of the words in the sentence, but only we get this light up where the word actually exists. That's why it's a bag of words, because we don't care about the order. Okay, so let's see how we actually implement that. We use sklearn or sklearn, which is one of the most useful libraries if you want to do simple classical machine learning. If you want to work with neural networks, so they do only kind of the basics of neural networks, and then you have to work with PyTorch or TensorFlow or Keras or your favorite framework. We can talk about that later on. Okay, so first of all, we are going to create our corpus, which is just the data frame, the one that we loaded previously, in the phrase, which is again just the text representing the conditions or the complaints, and we're going to take the values in this column. So that's what I did. And now we're going to initiate our count vectorizer. And according to your question, we have here stop words equals English, because we tell our method that basically we want to filter out stop words in English. So again, is, are, and all of these words are going to probably be filtered out. But it really depends on the implementation itself. And this count vectorize will basically, once we, just a second. Yeah, okay. So that was a problem. Just add the under bracket. Perfect. Okay, so after we initiated it, we now need to actually fit it on our specific data. And what is going to happen once we fit it? It's going to count all the different occurrences of the words in our documents, and that's how we train this bag of words model. So, train, amazing. Now we want to actually look at the vocabulary of the output, and I plotted here the most frequent words in our data, in our documents. And does that make sense? That's the most frequent word in our data. And zits, yeah, that's the second most frequent word. Do you think that makes sense, these two? No, it kind of feels like we have a problem here, right? Okay, so let's try to see how many times this actually repeats. What I'm doing here is I'm going over all the different sentences in documents, and I'm removing punctuation, and basically I'm splitting it into the different words, and I want to see if the word equals to this weird thing with these two dots here, or to zits. And if that happens, I want to print both the index and the text itself. And when I run it, I only get this. That's weird, right? Yeah, I think we can all agree that's pretty weird. Okay, so I'm not gonna go deeper into the implementation itself. What I would usually do if I were just me and not in a tutorial, I would actually go deeper into the documentation and try to see what happens, where is the bug, or maybe the bug is in the data itself and stuff like that. But here we're going to kind of do this whole bandage approach, where we just add to the stop words these two words because they don't make any sense. So, and then we reinitiate our vectorizer, we retrain it, and when we initiate it, we use the new stop words. We retrain it, and then we look again at the most frequent 10 words. Okay, that makes more sense. Right? No? Yes? Okay, perfect.
It's still weird that they're descending by exactly one for each time.
No, why W?
That U and U's are so similar to each other.
Let's see.
And it's also weird that all the words are with W and Y.
And how do we don't know that we don't have the same problem with the word young? It doesn't appear in only one sentence like before.
So we can do that, but I actually checked.
Okay.
That's like the simplest example. And now we're actually going to look at our data. So here it's sorted alphabetically and not according to the frequency. That's why we see 10 and 150 starting, because they're not the most frequent ones. And basically that's our embedding. That means that for each data point in my data frame, I'm going to use this matrix and just look at the sentence itself. And if the sentence contains accident, for example, I'm going to put 1 here. Okay, that's my implementation. And then this whole row is my embedding, my bag of words embedding for this data set, for this sentence. Okay? Perfect. So I don't care about the order in the sentence itself, but I do create about the order of the matrix, because that's my vocabulary. And I want this to be to remain constant, because these are my features. I'm going to train a classifier using that. So I want to have meaningful locations in the matrix or in the embedding. But bag of words is a very, very simple method. Can we do something smarter? And what do you think the answer is going to be?
TF-IDF.
TF-IDF? Okay, that's a very specific answer. I was aiming to yes. Okay, so we're going to talk about word-to-vec embedding, which is slightly more sophisticated than TF-IDF. So, word-to-vec embedding also requires a data set to train on, but the algorithm itself is smarter. It uses shallow neural network, which was developed in 2013 by Google. Is there anyone here who is not familiar with what neural network is? Not in the brain, in the computer? In the computer. Brain, which one do you know? Someone. Okay, so basically, neural network is a very powerful class of learning algorithms. It's basically, I can't really, I'm going to do it here. Basically, we have these neurons that are not, can you see that? Or is the podium, okay. So we have our neurons, which are basically just functions, and they're connected. I'm just going to draw the simplest neural network. I think they're all connected. No, they're not. Okay. And they're all connected, and basically what we want to learn is the weights here. So the problem with neural networks, unlike these classical machine learning algorithms, is that we don't have any good theory for that, but empirically it works, and it works much better than anything else that we have at this moment. So in the past few years, and when I say few years, I'm talking about more than a decade, we usually work using neural networks. But it has its own flaws, its own problems, but again, very powerful. And one of the problems is that neural networks usually require a lot of data to train on. So that's a major problem we need to consider, but not a problem for now. So word-to-vec is not based only on frequency, but it also captures context, semantics, and syntactic similarity and relations and things that we did not have with bag of words. And how does that happen? We basically look not only at single words and whether this word appears or not, but we also try to actually learn the context in which words appear. And that's how we capture these relations. Again, this neural network, I'm not going to go deep into that. But we're going to look at the implementation. So I'm importing all the relevant libraries and initiating my word-to-vec model. Now, do you remember Dafna's example from the PowerPoint with king and queen and woman and man? Let's take a look at that. I'm going to take two vectors, king and woman, and I'm going to just reduce the man vector. Let's take a look at the top 3 most similar tokens here, or words. Now, when I say most similar, I'm talking about cosine similarity between the different vectors. Amazing, right? Now, people use this example in the past decade way too much, and I'm one of them, as you can see now. I do want to stress that the closest vector is not really queen, it's king, but in the implementation of word-to-vec, it cannot return one of the vectors that are used as input. So, I mean, it's a cool example, but not perfect. But basically what it shows is that we can actually perform these mathematical manipulations in this latent space, in this embedding using word2vec, and we get meaningful things. And that tells us that this latent space is actually very informative, and it captures some of the notions that are in our world. Okay, so now we want to create our corpus, which is what I'm doing here. And do you know what dimensionality reduction is? Okay, the two words mean something. So dimensionality reduction is basically taking a vector of high dimension, such as word2vec, which is 300. I cannot plot 300 dimensions. If you think I can, please, you're welcome to show me. And I just want to plot our vectors. I want to look at the space. So I'm going to reduce the dimensionality. And I'm first going to reduce from 300 to 50 using PCA, Principal Component Analysis. That's a linear dimensionality reduction, which is basically trying to optimize the reconstruction error. So we are going to take the 50 the 50 directions with the most variability. And in that sense, it captures most of the information. And after that, I'm going to use t-SNE to reduce to 2 dimensions because I cannot plot 50 dimensions. That's probably the same problem with 300. And I do that because I want to keep also the local dependencies and not just the global ones. So after I've blubbed for a while, let's see our output. So this is our 2-dimensional latent space using word2vec. And we can see here, just, I'm plotting several examples, just 50 different words because I don't want to overload everything and then we can't really see nothing. And what do you think about this space? Do you recognize anything that looks meaningful? You can just shout. Sorry? It looks similar to the word cloud? Well, it contains the same words. So it makes sense. But I mean, I'm talking about the locations in the latent space. Do you see anything informative?
Cold and cough shows seem similar.
Sorry?
Cold and cough shows seem similar.
Oh.
Yeah.
Oh. Yeah, okay. So that actually, that's very meaningful. That's cool, right? And we also see feel, feels, feeling. Remember I talked about having this lematization pre-processing. So, okay, our model actually knows that these are very similar. Yeah, we see all the organs here. Perfect. Although food is a bit far away, but not very significant for us, this organ, probably. Okay, and now maybe let's plot a bit more. So instead of taking 50, let's take 100. Okay, so that's a bit messier. But again, do we see informative things here? I'm seeing left and right, which is cool. And again, we can see here. So the latent space looks a bit different because I reduced the dimensionality using more examples than previously. So the dimensionality reduction is a bit different. I retrained it. So that's why here now we see here our organs and not here as previously seen. But that's just a property of the dimensionality reduction. And apparently see, know, and think are very similar. So we see some very nice relations in our latent space. That's what I was aiming for. Okay, so that was, yeah.
Why are you using the PCA if you're going to use t-SNE?
So the problem with using just t-SNE is that it captures only local dependencies and not really the global dependencies. It's a common practice to use both algorithms, PCA for the start of the dimensionality reduction and then t-SNE. Usually if you use just one of them, so it really depends on how your data looks like. That's the whole idea of how do you choose the best dimensionality reduction algorithm. But if you have no assumptions about how your data looks like, it's a common practice to combine both. Yeah.
Question. Can you
you go back to the example about the king?
Yeah.
What is the quest? I mean, what is the query that you want to do? I mean, you are looking for some word that is closer to king and woman, that is far away from man. This is
So no, I'm taking the vector, basically the embedding, right? The vector representation of the word king, and I'm adding the vector representation of the word woman, and then I'm substituting the vector representation of the word man. So it's basically, again with the board, it's gonna look like the king vector plus woman vector minus man vector. And that's a new vector. Okay, so if, is there a...
Find the one that is closer to this king vector.
Yeah, exactly. So it's gonna be, let's assume that this is king and, I don't know, this is woman and, so king, woman, and man is gonna be here. So I'm gonna add this one and reduce this one, so the end result is gonna be probably, let's do it here, so that plus that and minus that, so it's probably gonna be here or something. Okay, and then I'm taking this new vector and I'm trying to find the nearest vectors to this one. So the nearest vectors, the most similar vectors in terms of cosine similarity between the different vectors are queen, monarch, and princess, which are all kind of, they have similar meanings, and this similar meaning is basically a female king in some sense. That's why we're saying, okay, you can perform these mathematical operations here and get meaningful things in this latent space. Okay. Are there any questions? No? Perfect. Okay, because now we're going to talk about the most complicated and sophisticated embedding method, which is using pre-trained language models. Now, a language model, before we're talking about pre-trained, a language model is basically just a probability distribution over different sequences of text. So it's a model that assigns probability to words or sentences or documents. But that's exactly what it is. It's a statistical model. It's nothing magical, although some people kind of feel that it does. And we in the past few years, ever since Google presented, I think it was 2017 or 18, so it was May 2018. I remember the month, not the year. So in May 2018, a new first brand pre-trained model was presented by Google. This pre-trained model is named BERT, which is bidirectional auto-encoder, transformer, all these words together somehow create BERT. I really don't remember the name because no one used that. And this model was trained on huge amount of data. And I'm saying huge because it's really something you can't grasp. They basically took a large chunk of the internet and book corpus and Wikipedia and everything, and they trained the model. Now it's not just a simple model, as you would think. It's a very complicated one. It's based on the transformer architecture, which has this attention mechanism that I'm not going to go into. But if you want to learn more, just come talk to me during the break. I think it's very interesting, but we don't have the time or the capacity for that. And anyway, this model basically captures the statistical relations between different words in the training data. Now, it's really good, really good, and that kind of shifted the entire field of NLP. And ChatGPT, which I mentioned earlier, is another form of pre-trained language model. Now you can use these language models as is, off the shelf, or you can also fine-tune them, which is another phase of training with much lower learning rate and less epochs. So you can fine-tune it on your downstream task. But in order to do that, you're going to need some more data. Now, what's cool about these models is that you can also use them as embedding methods. So you can extract this hidden layer from the neural network, this latent representation of the sentence, of the input data. And that's what we're going to do here. So we start by importing all the relevant libraries. That's fine. And we initiate our tokenizer. Basically, a tokenizer just takes a sentence and splits it into different words. Okay, so if we have the sentence, I went to the beach today, it's going to be I, comma, went, comma, to, and it's just going to split it into the different words in our vocabulary. And we're going to initiate our model. Just a second, it takes time. So here we see all this very complicated architecture that I'm not going to go into, but that basically specifies all the different layers that we have in our model. Again, very sophisticated. And we're going to aggregate all the embedding of the different sentences in our documents list. And I'm not going to go into why we need all of these things. Just basically what I'm doing is tokenizing all the data. And then once I have these different tokens, I map them into the indices they have in BERT's vocabulary. And then I use BERT in order to embed them. So I'm taking the output of BERT, the hidden layer. Now that will take about a minute, maybe less. And then we can continue to the same thing we did before. We're going to reduce the dimensionality. First, we're going to use PCA to reduce it to 50, and then we're going to use TSNE to reduce it to 2. Just going to take a bit. And we're going to just look at the embedding not of single words, but the entire sentences, because BERT is actually capable of doing that. Again, we can look at different words, but why not look at the whole sentence if we can. So we see this cute outlier here. When I remember her, I feel down. That's very far from all the rest. Let's see why. The other sentences are, when I carry heavy things, I feel like breaking my back. It's here, the orange one. There is too much pain when I move my arm. My son had lip pierced and is swallowing. It looks like all the rest are related to physical pain, and only the first example is related to emotional pain. So in that sense, it does make sense that it's very far from all the rest. And again, it captures the essence of the text itself. Let's take a look at the green one, which is a bit farther from the rest. There is too much pain when I move my arm. I don't know, it feels pretty similar to I have muscle pain that my back, or yeah, feels similar.
Too much?
Yeah, maybe. So you could, in principle, visualize the attention mechanism of BERT, which basically tells you which words were more meaningful in the prediction. We're not going to do it here. Again, we don't have all the capacity to do everything. Okay, so we talked about 3 different embedding methods. The first one is bag of words. The second one is our word-to-vec. And the third one is using a pre-trained language model. And BERT is just one example.
So,
Yeah.
whenever you clustering of the whole document, of the whole sentence just to word.
Mm-hmm.
So here you compute the embedding of each word, each token, sorry.
Mm-hmm.
And then how you aggregate all the embedding in each like this sentence.
Okay. So so basically in word-to-vec, you have the embedding of only one token. And then when you go to BERT, you also have this embedding for a single token, but you also have this very unique token that you insert, CLS. That token appears at the beginning of each sentence you insert into the model. And because there is this attention mechanism where you actually look at all of the tokens and you aggregate their meanings, so basically this CLS token, it kind of represents the embedding of the entire sentence. It was trained in that way. So in order to get this whole sentence representation, whole sentence embedding, we just take the hidden layer, the latent representation of the CLS token. Because otherwise we would have a varied amount of tokens per sentence, and then we kind of have to add this padding if we want to have this the same length of the embedding for everything. And this CLS token, the size is 768. So it's huge, that's why we reduced the dimensionality. So it's even larger than the Word2Vec, which was 300. Did you have a question? Okay, so we discussed 3 different embedding methods. Do you have any questions about them before we move to training the classifier? Okay, perfect. Okay, so now we're going to train the classifier. We're going to use sklearn, sklearn. That's a very useful package for machine learning. It's very simple to work with, and it contains lots of different classifiers and data processing methods and dimensionality reduction, clustering, accuracy matrices, basically everything. So we're going to use it. I just imported all the different libraries that we want. And let's start by looking again at our data. We have 25 different classes. These are our classes. You probably remember them because we kind of kept looking at them. And now we want to split our data into train and test. Now, why do we want to do that? You can shout.
Evaluation.
Evaluation. Okay, what does that mean?
On the overfit.
Overfit. Okay.
Estimating how well the model can generalize new data which is not in the training distribution.
Okay, perfect. So we train our model, and then we want to know how well it will actually perform on new unseen data, because that's what we want our model to do, right? If we just want to be great on our training set, well, we have all the data, we have all the information in the world, right? We're good. But the problem is that it's not only information that we can get, it's just a sample from the entire population, and we want to see how well our model actually understands the behavior of the entire population. That's why we put aside a portion of our data, and then we want to see how well our model performs on this new unseen data that wasn't used for learning for the training phase. So that's why we split it. So the size of my training data is 635, and the test data is 71, which is 10%. So I split the data into 90% training and 10% of test. Now, before we start training our model, I want to verify the different distribution of classes across both train and test data. So that's exactly what I'm doing here in my plot. This is a function that plots the different classes out of all the 25 classes that I have according to train or test. So let's take a look. That's what we have here. Now, are you happy when you look at that?
No,
No, why not?
not the same distribution.
Okay, I have no idea who said that, but you're right, yeah. So the distribution between the train and the test of the different classes is very different, and that's a bit weird. So how about we balance it? Okay, so that's what I'm doing. I'm just balancing it. And now let's take a look. Are you happy now?
What do you mean by balance?
It means that, okay. So here, I have the different classes. I just didn't label them. But that's one class, and I'm looking at the distribution. What is the count? How many do I have for the test set, and how many occurrences do I have for the train set? And that's really not balanced, right? Because this class is overrepresented in the test set, but underrepresented in the train set. Now I wanted the train and the test set to have about the same distributions. In that sense, that I want my data, both the one that I train on and the one that I test on, to follow the distribution of the entire population. So I don't want to have these very weird.
Big gap.
Yeah.
Okay, thank you.
Sure. So I balanced it, and now it looks better. It doesn't have to be the same, but I don't want to have these very huge gaps.
I mean, in some classes you have lesser values, and now they are more or less the same.
Yeah, so now per class, the train and the test are similar. That's okay that I have here overall less examples than here, because that's my data.
What I was meaning is that in the previous graphic, you had less value for the class there. No, I'm sorry. So
Okay. Now, that might be a good time to say that usually when you train a classifier, you do not want your classifier to learn the distribution, to learn only to mimic the distribution of your data if the data is very unbalanced, in the sense that if I'm trying to detect this very rare disease, so the positives are going to be, I don't know, like 1%, and then the negatives are going to be 99%, and my classifier can get 99% accuracy, but just say no all the time. So it learns the distribution and it doesn't learn the signal that I have in the data. So when you have these very extreme cases, you want to balance your data, and you do that by either undersampling the majority group or oversampling the minority group. And there are tons of works about how to do that right. It's an unsolved problem, so if you're looking for something to investigate, go ahead. Might be useful for me. Okay, so now let's take a look at our, let's start by training our classifier. Again, we're going to work using random forest classifier. Is there anyone here who is familiar with decision trees? Anyone who's not familiar with decision trees? Okay, yeah, so just people who didn't raise their hands, so I don't know. A decision tree is a classical machine learning classifier. It basically partitions our space each time with a binary question, yes or no. Does that feature cross a threshold, yes or no? And then we start with these partitions. So for example, if we have a 2D space, yeah, that kind of works. So we start by asking, is the y value higher or lower than this value? If yes, one class, if no, other class. And then we continue until we have all the data points classified correctly, or until we just exceeded our gap. Okay. Now, decision tree is not perfect, so we're going to use random forest. It's basically just an ensemble of decision trees. As you can see here, we create different decision trees, and in our example, it's going to be 100, and we take the majority vote of the decision trees. Why use an ensemble? Because again, it just improves our prediction. We have different initializations, and sometimes, and because it's a greedy algorithm, so sometimes there are different partitions of the space you could choose. So that also adds some random aspect. So in that sense, taking the majority votes, creating an ensemble is more robust. Okay, so how do we do that? We start by importing everything, and here I know I skipped it. I just created a class of transformer embedding. That's for the BERT classifier. And now I want to initiate our random forest model. I'm going to use both bag of words and BERT embedding, and the same classifier, random forest. And I'm going to train them. Here, BERT is going to take a little while. So we're going to wait. And after they're trained, I'm going to check their error. I'm going to check their accuracy on both the training data and the test data. Now, do you have any hypotheses on what's going to happen? Wait, I don't want you to see that. Which method do you think is going to be better? Bag of words or BERT? BERT. On which data? The training or the test? Both. Okay, that's a reasonable prediction. I agree, but that does not happen here. Now, I do have some hypotheses on why, but it's not here. Okay, so we have the accuracy of the bag of words on the training data, 91.5%, pretty good. And the same bag of words model on the test data is 70%. It means the model is right on 70% of the cases. Again, guess level is not 50%. We have 25 different classes. So it's a pretty hard task in that sense, or at least guess level is really hard. And then, I shouldn't play with the parameters here. Just a second. I played with it. So we're going to see it in a second. So, why do you think BERT should be better?
Better price for learning from rare words or subwords, assuming that they're similar in their usage.
Sorry?
Better has better price for words which might appear only once, so a note the bag of words model count on NLP format. Word model is seen that multiple times, and the embedding can map similar words together.
Okay, so BERT is more holistic. That is correct. And here we're talking about the medical domain. So our bag of words model is actually a model we trained specifically for our data set, right? We actually trained it using our data. And BERT is an off-the-shelf language model, which we did not fine-tune on our data. So in that sense, although it is very sophisticated and gathered some world knowledge, it's not tailored for our task. So in that sense, it's kind of a trade-off. Okay, so what we see here is basically that bag of words is pretty good and generalizes okay. And BERT, I kind of destroyed it now when I played with the parameters. So I'm sorry about that, but you can just play with the alpha coefficient or just remove it back to the default, which is 0. You can do that in your notebook later on. I'm just not going to wait more for that. And now we want to actually look at the predictions per sentence. So let's just sample a random sample. And we're just going to look at the prediction per sentence according to both of our models. I just want BERT's model to finish its training, and then we can do that, because otherwise it's not trained. Okay, perfect. So, it's going to work in a second. In the meantime, any questions? Okay, yeah. So now when I don't destroy things with my parameter plane, we can see that the bag of words classifier is at about 92% accuracy on the training data, and BERT is at almost 100 accuracy. Did anyone say overfitting previously? Feels like overfitting. Okay, let's look at the test data now. So, bag of words, a sharp decrease from 92% to 70%, and BERT, an even sharper decrease. Now, again, guess level is not 50, so that makes sense. It's not worse than guess level, but still, that's a very sharp decrease. Again, feels like overfitting because it's more complicated. And the dimension alpha is larger, and we have really just 661 examples for the training. Okay, so now let's just sample randomly a sentence, and that's the sentence that we sample. I feel pain in my back while I'm working. Now the true condition, the true label is neck pain, and that is the distribution for bag of words across the different classes. That's basically the probability that the model assigns, the random forest using bag of words embedding, assigns to the different classes. And we can see that it's pretty well knows with 82% confidence that it's neck pain. And now when we move to BERT, we see, well, BERT is less confident. We see higher density for the joint pain, which is very much relevant. And we can sample again and play with that. That's really easy. You just rerun both. So now we have the sentence, oh, my heart hurts me. I try to calm and I can't. So again, heart hurts. And we see here for the bad words, very certain, and for dirt. Okay. Now we want to look at where the models get it wrong, where they misclassified examples. So we're going to sample just an incorrect example, a misclassified one. And we see here this shoulder pain example, which is I feel, that's not, so the, sorry. I feel a great pain in my shoulder joint and it does not go away. So the true label is joint pain. And our model, bag of words based model, believes it's a shoulder pain, which makes perfect sense. As I said, the data is not perfect. And another sentence, I think I sprained my ankle, it really hurts. So the true label is injury from sports. And then the bird-based models believe it's an infected wound, which does not make much sense. And you can see it's all over the place. It really doesn't know what's going on. Okay, so now I'm just inserting a new unseen.
Return a confidence or just the answer? Giving an answer and how confident is not in that?
Yeah, so that's the confidence. That's the distribution according to the different classes. So if you just want to return the class and that's it, the final prediction, you take the one with the maximal value. But here you can see the actual distribution. So that's basically what our model thinks. And if the distribution is really kind of all over the place, so it's very confused, it's considered to be a harder example for our classifier. But also here you see that there are two kind of competing classes, which are joint pain and shoulder pain. But in this example, the model is pretty certain, right? Okay, so now I just, took a sentence, it's not from the data, and I want to see how the models will classify it. So this is a bird. So the sentence is, it hurts when I lie down, I can't sleep. And birds believe, bag of words believe it's a back pain, and you can see the distribution. And the bird one is all over the place, and it says body feels weak. With a very low confidence, by the way, only 10%. Okay, so now we want to actually look at our different models and try to understand why they made mistakes. So we can plot the confusion matrix. Now, a confusion matrix is basically the different classes. This is the true label, and this is the predicted label according to the model. And a perfect classifier would have an all diagonal numbers, which are not zero, and everything else would be zero. Does it make sense? Yes. Okay. Why? Because it means that whenever the true label was back pain, the model always said back pain, nothing else. So you can see here that the model makes mistakes, as we know that happens. So that's the confusion matrix for the bag of words method, and we can see that it usually makes mistakes towards thinking that something contains blurry vision when it's not. That's kind of the things that I see most here, and also heart hurts. So we see that the model mostly thinks that that these two conditions are more firm than they are. I do want to stress that we don't see any specific inter-class confusion. We don't see, for example, we kind of see that when the true label is emotional pain, our model thinks that it's a blurry vision, but it's only 2 examples, so it's not really significant. Overall, we don't see that there are any 2 classes that kind of compete and make the model confused. And we see that for BER 2, again, it had lower accuracy, so it makes sense to see the diagonal, which is a bit off. But again, nothing really specific. And now we want to look at feature importance. Now, feature importance basically tells me how important the different features that I inserted into my model. Now, for bag of words, it's very interpretable and intuitive. Why? Because my features are just words. So according to the location in my embedding matrix, I know which words were meaningful. And for birth, it's not as simple because it's a non-linear neural network. So I'm going to plot only the feature importance using the bag of words method. And we can see here the top 20 features according to birth. These are the most important words for the random forest with the bag of words embedding classifier. When I say the most important words, I mean the words that were very useful in order to reach a decision regarding the class. So we see here ear, shoulder, neck, knee, heart, hair, stomach, and most of these words actually correspond to the different classes that we have, right? We kept seeing that we have this shoulder pain and neck pain and right, these all divisions into classes, and we can actually look at the different yeah. So these are different labels, and we can see heart, we can see shoulder pain, we can see stomach ache, knee pain, right? These are actually my classes that I can see that the model learned to use. So it's really cool and very informative in that sense. Now, we do have 20 more minutes, and I can go into another topic. But before I do that, do you have any more questions?
Do you think what happened between the birds, the low accuracy and the high accuracy?
Yeah, so basically, just a second, where it is. Oh, wow, it's been long. Okay, yeah, so it looks like a really classic overfitting here in the sense that our training accuracy is almost 100%. And then we see this, oh, you can't see that. We see this very sharp drop in the test data. And that's why I started playing with the parameters.
Before that, you had 0.05 accuracy per word.
In the train data?
Oh.
No, so, okay, I'm just gonna refit it. So we can see here the train data, and then for the bag of words embedding, it's 92% accuracy. And for BERT, it's 99.9, that's why I'm saying almost 100. And then for the test data, the bag of words one is 70%, so we see a drop of 22%. And for BERT, it's 33.8, which is a much sharper drop. And that makes you wonder, okay, do you even generalize? And I would say no, not that well. Basically, it looks like a classical overfitting. It does require some more analysis in order to verify that, and that's why I kind of started playing with the different parameters, but we had all these technical issues that I didn't have the time to do that. But from what I did play a bit, it appears that if I prone my random forest, it does improve the accuracy on the test and reduce the accuracy on the training data, which is exactly an indicator that I'm overfitting right now. So if I prune the model, it does help. And pruning is a method to make the model less specific, less complex, and it's very useful in order to prevent overfitting. I mean, pruning for random forest, it doesn't work for all classifiers. So it does look like that, and also another reason is that the embedding of the bird is larger, and we have only less than 700 examples. So in that sense, it feels like there are too many parameters and not enough examples for our model to actually learn. But good question. We can explore. Okay. Any more questions? Yeah. Yeah, so I just used the default coefficient, the alpha coefficient, the default one, which is 0. But yeah, I can just write it here. Yeah.
So the pruning you were referring to is maybe early stopping?
So early stopping is one way to prevent overfitting. You do that when you use gradient descent-based optimization methods. That's not what we're doing here. Pruning for a random forest is basically just stop creating, okay, I'll just show you. So if we're talking about one decision tree, so we have all these different yes, no questions, right? And that can be very deep. So, I'm just gonna, do you all see that, right? Yeah, okay. So pruning basically means I'm gonna stop. I'm gonna just cut it. And there are different ways to do that according to the weight, to the improvement, to the just how many edges did you have on the way. But basically that's the notion of pruning, is just making the model a bit simpler. And why does it make sense to remove only the lower leaves? That's because it's a greedy algorithm that created my tree. So here is the most, I mean, if you go up, you improve your prediction more than if you look at the bottom. Okay. Any more questions? So, maybe now would be a good time for you to actually do things on your own. Yeah, I know, it's scary. So, do you remember I was talking about lemmatization? You can open the file. It's called lemmatization.ipynb. Python notebook. Okay, so we were talking about in the word cloud about the fact that there are different words that should be merged together, right? So for example, cough and coffee, right? Motivation is clear? Because we get the distorted image here, right? We would like to merge these two and count them as the same and aggregate their probability. And then cough would look even larger. And that's okay because it actually represents the real meaning, the real essence of my data. Okay, so that's what we're going to do. We're going to do lemmatization, which is basically a way to identify the underlying meaning of the word. Now, there are two ways to do that. Stemming is one. We're not going to look at it, but it's basically just heuristic that moves this S and this ing. We're going to do something which is a bit more complicated, and it's based on the part of speech. Okay, so we start by just importing all different libraries, and again importing our data. Here you're going to get an error because the data is not in a data folder, so just remove it again. Remove that part. You can do that in the rest of the files on your own. I trust your judgment. And again, we want to look at the classes. Again, we have 25 different classes, and we split the data into train and test. Oh, just a second. What did I not do here before splitting the data? Perfect. Someone was paying attention. Yeah, so I'm going to just take this from the other notebook and remove duplicates. Okay, and train test. Okay, perfect. Now I'm going to initiate my lemmatization, and I'm going to just use this input sentence for the sake of our example. So the original sentence is, I have been dizzy for many days, and the output after applying this lemmatization is, I have been feel dizzy for many days. Does that sentence make sense grammatically? No, grammatically, does it make sense? Yeah, it feels like, would you say that? No, okay. Yeah, but it is the simple form of each of these words. So instead of having been, we have be. Instead of feeling, we have feel. Instead of having days, we have day. So in that sense, we did get what we wanted. Let's try to play with another example. Anyone want to shout a sentence? A problematic one? No? Okay, so what we see here is that hurted became hurt. Perfect, that's what we wanted, right? Okay, amazing. Now, we can again fit a classifier, but here, oh, I did not invert that. Don't do things late at night. Okay, so what we're going to do here is basically train we're going to train two different classifiers. The first one is not going to use any of this lemmatization that we created, and the second one is going to use it. And we don't need to have 1,000 estimators, let's train it faster. So again, two models. One uses the embedding after doing this pre-processing phase, and the other doesn't use it. Let's see what's going to happen. And this is my accuracy. So accuracy without doing this pre-processing phase is about 65%, and with doing that is 67-68%. So we see an improvement. I'm not saying it's a major improvement. Oh, and this is on the test data set. We can also do that for the train if you want to. Let's do that for the train as well. So it's going to be X train and X train. And what's going on here? Oh, X train. Okay, and these are the accuracies. So we see that we basically did not have to suffer from any training error, but we did get an improvement in our generalization, which is really cool. And that we did by only doing this lemmatization, basically taking different words into their simplest form. Now, your turn. You're going to plot the word clouds after doing the lemmatization itself. You have 10 minutes, so you can play with that. You can do that afterwards too. There are also two other notebooks here that you can play with afterwards or never, up to you, whether you want to learn or not, I'm just saying. The first one is part of speech tagging. It's basically the different parts of the words in the sentence, such as noun, adjective, verb, and stuff like that. There are 8 different parts of speech in English, and basically I'm just going to run it super fast to show you, because you're going to play with that afterwards on your own. And basically what we do here is we get a sentence, and then we can split it into the different parts of speech. We can tag it. And we do that using NLTK, which is a natural language processing toolkit. Very cool. So you can play with that too. And again, here you have another task where you can just create these word clouds that we had in the beginning, only for the noun phrases, which are usually more informative, because if you remember previously we had, just a second, word clouds. So we had here under emotional pain, do you remember that we talked about this break where I said it should probably be breakup? So if you look at the noun phrases, A, you don't get all these adjectives that are sometimes not very informative, and B, you get break up and not just break. So it basically shows you things that are more informative taking these noun phrases. Yeah. Sorry? It should be here, but again, yeah. Maybe it's just my hypothesis that it's a breakup. Yeah, it can be just.
Take a break.
Yeah, it can also be other things, but it's really hard to tell without doing this analysis. So that's just my hypothesis. I'm thinking about breakups. I don't know. Maybe it implies something. What? Yeah, what would Freud say about it? Okay, so yeah, you could do that and actually see whether my hypothesis holds or not. So that's the part of speech tagging. And topic modeling is an unsupervised method that we try to cluster different data points together according to the topic that their text represent. Again, don't have much time to go into that. You have all the functions here. We're using TF-IDF and different algorithms, NMF, NLDA. I can talk about it during the break if you're really interested because we don't have much time. And basically, you can see here their output. You can see the different topics where the model kind of clustered the different examples, the different topics. So one topic contains words such as pain, sharp, stomach, neck, shoulder, joint, feel, knee, muscle, and foot. The other topic is feel, dizzy, body, weak, stand, like, heart, cold, sad, no. And I'm not saying it's perfect, but you do see some signal here. Using the LDA, it's usually better. Let's see. Skin, wound, face, cut, vision, think. No, it's not better. No. Okay, and these are the different sentences that kind of created the topic. And in this, I would start by plain understanding more what the topic modeling is, what the different methods are. You basically have it all here, and you can use Google. But in general, we create a function to display the different topics. It's just printed everything. We load our data frame. We define the number of our features, and we start by initializing our NMF, which is based on TF-IDF. Do you know what TF-IDF is? I'm just okay. Yeah, so maybe ask me. TF-IDF is basically a measure to say how much something is similar or different from other topics. So it's basically the amount of unique words in a document divided by the amount of by all the other words in the in the other documents. So if I have one document, I want to look at the words in this document, and I want to compare it to the words in the other documents. And then the words that are very unique, they kind of describe to me the document in terms of how different the document is, because there are lots of repetitions in the terms themselves. So I want to find what's unique about it.
Given that I'm representing as a vector, or can I work with different?
No, you can work with words. Yeah. Yeah. Okay. So we don't have much time. We have 4 minutes. Now would be a great time to stop and ask if you have any more questions. And you can also come during the break. I'll be here now, but, but that's probably 8 because I'm not going to come tomorrow. You do have my email because I sent you all the data and the files. You can contact me if you have any questions regarding that. I'm fairly available via email. And that's it. Thank you.
Thank you.